who is going to give the first talk on nearly critical superfluids and holography.
Okay, let me start by thanking the organizers for this great opportunity. I'm really happy to be here, and I have enjoyed the talk so far. Right, so today I'm going to discuss a few papers that came out with Christiana and also with Polydoros, who is a postdoc at Durham. And there is a lot of work in progress related to these topics, but I cannot open my mouth about this, so I will just have to give you the results we have already published. But we keep on doing some work along those lines. So in the beginning of the talk, I will just motivate the topic, and I will give you a short introduction. It will be about nearly critical superfluids, so superfluids which are very close to the Ferris transition. And then I will talk about field theory considerations, or constructions that you can come up with in just field theory terms. And this is why I say n less than infinity. And then we will just take, we will have some pretty much general theory from that. We will take n to infinity. That will drastically simplify things for us. For example, thermal fluctuations will just die out completely. We will not even care about them. And we will consider a holographic model. And so in this classical limit of these field theory constructions, we will see that precisely the holographic model reproduces those theories, and we will actually be able to compute some transport coefficients that we will just pull out of a hat when we do our field theory constructions, right? So we will see how these are fixed in a holographic model. Okay? So what is the motivation? So the usual motivation, if you want to study something holographic in applied holography, is that you're looking for some kind of universality, right? So you want to extract some information from holographic theories, which should apply to more general systems in nature and not just holographic systems. So in one of those regimes is, of course, the hydrodynamic regime, right? So you take, you look at energy levels which are much smaller than the temperature scale in your system, and you would expect that, you know, given the strong coupling of those degrees of freedom, that you don't have quasi-particles that live long enough, and that you are only left with the conserved charges of the system, right? So, and those dominate at long wavelengths all the dynamics of your system when you are especially close to thermalization. Another way to look for universality is close to phase transitions, right? So in that case, you are actually looking at critical points, at fixed points. There is a correlation length in your system which actually diverges. This is dimension full. It diverges, it goes to infinity at exactly the critical point, and at that point you expect to have some kind of scale invariance. And you know that scale invariant theories or conformal field theories are quite rare. So there is, they are usually discrete fixed points, right? So and you might wonder what holography can tell you about all that. Well, strictly speaking, in the classical limit of holography, you're not expecting anything else other than mean field theory, right? So all the thermal fluctuations will die out. You will get some mean field theory, but even that classical part is a good start so that you can put noise on top of it, or you can do Kelty-Swinger. You can make it into something more realistic. Okay, so I decided to talk about the field theory construction in two different modes. The first mode is the microscopic mode, okay? So in this microscopic mode, I'm imagining that there is some relativistic field theory with a global U1 symmetry, and somehow we have brought it up to some kind of finite temperature and chemical potential mu. So there is this charged operator under this global U1, and right below a critical temperature, for some reason, and without any explicit deformations in the system, your charged operator decides to take a non-zero vacuum expectation value. And you can imagine that you have some current, your charged operator, and you can introduce external sources in your theory. Okay? Now, if you are strong enough, you can take this microscopic theory, you can compute the generating function, And that will be a function of the background metric that you put your theory on, the external gauge field, and also the external sources for your charged scalar. Now, if you start taking derivatives with respect to those external sources, you will discover the stress energy tensor, the current density, and also the VEV of your scalar operator. Now, if in addition you are thinking you are a sensible person and you want to say that this A mu is actually the electromagnetic field, you will want this generating function to be invariant under gauge transformations of the external field. Okay? So the theory has a global U1 symmetry, but it is invariant under gauge transformations of the sources. Okay? That's different. Now, just because your theory is invariant under gauge transformations, you can show that there is a nice word identity, which, if I don't have any sources for the scalar, that would just be the current conservation. Okay, but if I have sources, then you have some sources on the right-hand side of this equation. If you are invariant under coordinate transformations, just reparametrization invariance of your theory, you know, I change coordinates, I get the same generating function. Then you can show that you have basically another word identity, which, if I don't have any sources on the right-hand side, F mu nu is the stress tensor of A mu. Then that could be what we call the conservation of the stress tensor, but if you have sources, you get modified to something like this. Okay? Good. Now, let's say that we're far away from any critical point, okay, and we are in this broken phase. Now, in a hydrodynamic limit, where you consider only long wavelength excitations of your theory, you might expect that you can express the stress tensor and the current as a function of some local temperature, local fluid velocity, and local chemical potential. Then you take these expressions, which are the constitutive relations that you will write down, you plug them in the word identities, which become the equations of motion. You can find that's a closed system now, and you can solve the system nicely. And if you are in the broken phase, you have to include an additional player, which is the phase of the condensate. Okay? So the phase of the basically, if you think about it, these are variations, thermodynamic variations, which you make local of your system. And this is just a transformation of the system that leaves the free energy invariant, right? So if I make if I make long wavelength variations of this phase, that buys me another light mode, another massless mode, which is the Goldstein mode. So in addition to writing these constitutive relations, you also have to write some equation that relates this phase with the chemical potential. I have this plus ... because you can change frames, you can change hydrodynamic frames, and you can basically change whatever is down here. But this first part is fixed by gauge invariance. Okay, there is nothing much you can do about that part.
So,
yes.
Here, before you introduce the condensate, sorry, do you also want to write constitutive relations for these O operators? Because otherwise the system is not.
You can do that.
Yes.
Yes.
You can do that.
You can, yes.
You have to do that, right? I mean,
Yes, you have, absolutely, yes. For example, I mean, yeah, they do enter here, for example, right? So it's not closed anymore. Good, so as long as, and you know, the gap, there is also a gapped mode in the system coming from the amplitude of this condensate. It's not just the phase. But as I'm moving away from the phase transition, that gap becomes big, and so it's this degree of freedom. You can integrate it out from the system as well, and then you end up with the usual superfluid hydrodynamics. Okay. But in this talk, I want to stay close to the phase transition and actually write down an effective theory which includes this amplitude mode. Good. Now, for simplicity, I'm going to basically completely ignore the dynamics of the stress tensor and the conjugate variables, which is the temperature and the fluid velocity. You might think this is too much, but this is how people have been treating the system during the 60s and the 70s, and they are just writing down effective theories for the phase, the amplitude, and the chemical potential, right? And I'm just going to stay focused on this coupled sector of charge and the order parameter. Now, in the normal phase, right, so before you enter this, this broken phase, you can write down constitutive relations for the charge density in terms of the chemical potential and the current. Now, what this term here is doing, basically it wants to restore equilibrium in the system, thermal equilibrium, right? So it wants to make the chemical potential everywhere the same. So whenever you have a disturbance in the local chemical potential, you get immediately a current that basically wants to push the charge back to its equilibrium position. Okay, so this is where this term is coming from. Now, there is terms which I'm ignoring here because of this statement. For example, there is another mechanism that if you take a bulk of charge and you give it momentum, then you will have another term in the current. But I am ignoring this mechanism altogether. So this only takes into account the mechanism that wants to restore the same chemical potential level. Okay? Now, another way to think about this normal phase is that let's say that we are right below the critical temperature, right? And I take K, or the wave number of the system, to be large, much larger than this gap. Then the physics I should see should be that of the normal phase. Okay? Now, when I am in the superfluid phase and my wave number is very much smaller than the gap of the system, then I start to see really the superfluid, right? So there will be an additional term, for example, in the local current, which will give me a persistent current. It will not want to decay even at equilibrium. Okay, and that's proportional to the spatial derivative of the phase of the condensate. There will be more terms. These terms all depend on the local frame that I'm using. But if I say that nu is equal to the time derivative of this condensate phase, then this extra term with an extra transport coefficient will show up here, and that's called the third bulk viscosity of the superfluid. Okay? Good. So if I take these constitutive relations that I wrote down and I plug them in the conservation equations, then in the normal phase I will just discover a diffusive mode, charge diffusion. Right? So I'm just doing linear perturbations. I'm Fourier transforming my local fields, and I discover that I just have charge diffusion. In the superfluid phase, I have a propagating mode actually, right? And this has a specific, it's like a sound mode, it's called the second sound, and this has a very specific speed of sound. By the way, I forgot to tell you that this susceptibility that shows up here was what we call the current susceptibility, and it is non-zero for superfluids. Okay, so what distinguishes the superfluid from the normal fluid is basically a non-zero charge susceptibility, current susceptibility. Okay, so now you might wonder, we are in two very different regimes, right? So how can I go from this to that? The answer is you cannot. So someone could imagine that as I'm going close to the phase transition, this chi jj will go to 0, and then apart from this factor of 1/2, then I will just get that. But this is not what happens actually. At least in mean field theory and in holography, chi jj does go to 0, but the third bar viscosity actually blows up. And the result is that this product here remains finite, okay, as I'm going to the phase transition. So I'm never going to get this from that unless I know how this regime where k squared, unless I know my theory well, in this regime where k squared becomes comparable to omega gap. Okay, so there is something missing from these two descriptions so that I can go from one to the other. So what is actually happening? You might have already guessed it. So at temperatures much lower than the critical temperature, you have your hydrodynamic poles. Okay, so for small k or for small wave numbers, they sit somewhere around the origin. But there is also a Higgs pole, or a pole, a mode that is related to these amplitude oscillations, right? So, and as I'm far away from the critical temperature, this is somewhere down in the imaginary axis. However, as I'm going very close to the phase transition, this mode starts becoming massless, right? So, and it is becoming hydrodynamic itself. So it's something that I should take into account in my description. And this blowing up of the third bulk viscosity that I talked about here has to do precisely with some degrees of freedom becoming massless, and I didn't have in my description. So if I take that into account, somehow this should be cured. Right? So I will have a much richer theory with more degrees of freedom. Okay, so how do we think about the effective theory? Now it's a different level. We are not microscopic anymore. Okay, now we start talking about effective theories. So in an effective theory, you basically have to identify some quantity that you will call the order parameter. You decide to introduce a UV cutoff in your theory. You basically, you say, I'm interested in energies up to here, and then everything above that is going to be integrated out. Okay? So that psi, or that psi, is very different from this O psi that we were talking about before. Okay? That was a microscopic operator. This is an effective degree of freedom, effective theory degree of freedom. So then at long wavelengths, after you integrate out, all this UV stuff, you end up with a specific probability distribution, which will be the Boltzmann distribution. Okay. Good. So that's at the level of thermodynamics. Okay. We want to go a step further and discuss dynamics. So what is this W naught? That's the Ginzburg-Landau potential, basically. It's quartic potential. You also have a term that is telling you how much free energy you add to the system by deforming this order parameter psi. And the parameters A prime and B are such that when I'm above the critical temperature, there is no condensate for psi or for psi. And as I go below the critical temperature, then a condensate has started to form. That, a non-zero condensate will give me a configuration of lower free energy. Okay? And in this way, you could say that you have a second-order phase transition. However, this is all at the mean field theory level, right? At the classical level. When you do this computation, you normally want to also take into account the fluctuations, okay, above the semi-classical approximation. When you do that, you will discover that the thermal fluctuations are actually much stronger than this, close to the phase transition, especially if you are in D less than 4, or if you have a finite n, if you have a finite number of components for this condensate psi. Okay? So this is a complication which actually changes entirely the nature of the fixed point. We will not worry about that today. We will be discussing holography. Okay? N will be infinite. Okay, so how do you go about discussing the dynamics of this thing? Right. So before talking about the order parameter in combination with a conserved charge that comes with it, let me just focus on a scalar order parameter. It's just a simple story. Let's say that you just had scalar order parameter with no current associated with it, with one of its symmetries. At thermal equilibrium, this should be a minimum. Okay, the free energy should be minimized. So that would be 0. When you're a little bit away from thermal equilibrium, you know that at some point you will start having non-zero time derivatives for your order parameter. It will want to go back to equilibrium. And the coefficient that relates one to the other is a new transport coefficient. It is called the kinetic coefficient gamma naught. Okay? So this is something you don't know from first principles. It's a number. You don't know whether it's going to zero close to the transition. You don't know anything. Okay, it's a number. Now, to deal with the thermal noise that we have integrated, coming from the degrees of freedom that we have integrated out, you say, okay, that those degrees of freedom dive very fast. Okay. So you can say that you will add this term here, which will just be Gaussian noise, and you are just looking at the dynamics of this thing. Moreover, if you want, I mean, you can write down a Fokker-Planck equation or a forward Kolmogorov equation, and you can actually relate this coefficient that gives you the statistics of this white noise, this D, with this, you relate it with this gamma naught, and this is one of the first instances of an Einstein relation. Now, if you take into account the current and you say that psi is really a complex order parameter, you have to write down some kind of conservation equation for the conserved charge, conserved quantity m. The derivative of W naught with respect to m will be precisely the local chemical potential. This extra term here is nothing but the Josephson relation that you have to write between the chemical potential and the time derivative of the phase. And that forces you to actually write this extra term that shows up in the current conservation, and the combination of this and that term do not change the value of the free energy in a time evolution of the system, right? So this is not dissipative, basically. They just couple the two modes. The dissipative terms are this one and this one. So I will talk a bit more about here, about that term. So what is that term? So if you express the free energy in terms of some free energy density, and you basically expand this term, you can see that this guy over here is nothing but the divergence of the current, right? So the first term will give you charge diffusion, the second term will give you the supercurrent, and these are actually the sources coming from the scalar, plus some noise. Okay, so you can, this is a good start. You can promote this to Kelty-Schwinger, you can bring in higher order terms, and we have actually done something like this with Polydoros. This is a holography talk, I'm not going to talk about that. So if you want to do this in holography, what do? So you basically have to construct some geometry, which is a planar black hole, right? So the temperature of you have the temperature of the black hole, and there is some bulk scalar which takes a specific value on the horizon. This will be the broken phase. There will be some gauge field in the bulk that you will use to introduce chemical potential in the system. The charge scalars will have no sources. We are spontaneous after all. And I want to stress that the flux of the gauge field through the boundary of your ADS spacetime gives you this conserved charge density rho. And you can define some flux of the gauge field through the horizon. Okay? Now, when you have a condensate, because on the right-hand side of Maxwell's equations there is stuff, this charge and this charge are not equal. When you don't have a condensate, this charge and that charge are the same thing. Okay? But this will show up later. Okay? You can define it, but just by looking at the geometry, there is no reason to define this quantity, but you will see its value later. Now, a model that, a holographic model that can actually capture what I'm saying is, you know, you don't have any metric coupled here. All the black hole is coming as a background. And you can introduce some neutral scalar in the system so that you can have additional scales and break scale invariance, which is annoying when you want to say something general. And global symmetry translates to gauge symmetry in the bulk. Now, I have to be very fast. So we came up with a recipe with Christiana and Polydoros at some point, and we can extract easily constitutive relations in the context of holography. So if you have the on-shell bulk action of holography, and you want to extract some VEV, you basically vary that action with respect to the bulk fields, and what you end up with is radial derivatives of the bulk action, derivatives of the bulk action with respect to the radial derivatives of the fields close to the boundary. And you can treat this as some kind of momentum density. So basically, you want to extract these numbers. One way to think about it is the symplectic current of gravity. Just because your theory is coming from a Lagrangian, you can show that the symplectic current is divergence free. In order to construct it, you are comparing two perturbative solutions, and if you are clever enough and choose these perturbative solutions in the right way, they can actually give you a lot of information just because of this fact. Okay, you can relate stuff to the horizon of this, to quantities that have to do with the horizon of this black hole. So to construct the hydro modes, you start your perturbative expansion. These are usually some thermodynamic variations. I mean, essentially at k equals 0 exactly, you want this to become either a thermodynamic variation or a variation with respect to symmetries. And what we discovered was precisely the model F that Hohenberg and Happerin had written a while ago. This free energy is, of course, fixed by thermodynamic quantities, but I want to tell you that this kinetic coefficient is now related at exactly quantities that have to do with the black hole horizon. I don't think I have the time to tell you much more. I'm still optimistic. But yeah, so one of the questions that we are asking now with Polydoros is to include the fluid velocity and the local temperature of the system, so move away basically from the probe. And after you do that, you want to go to Kelvin-Schwinger and look for new fixed points after you include noise into the system. So that's all I wanted to tell you. Thank you. Yes.
The broken phase. So, like the gapless modes are invariant of the choice of frames in hydrodynamics?
The modes themselves, yes, they should be. I mean, the dispersion relations you get. Say that again?
Is the Higgs mode, even though it's gapped, is it completely invariant under the choice of like Landau frame?
Yeah, I mean, it's gauge invariant. It's okay. So anything that you compute after you plug it into the constitutive relations, it should be independent of the frame you're choosing, right? So these are actually observables. Change in the hydrodynamic frame is just the same description, but the physical observables should be invariant under those changes.
Thank you. So, do you have a can you give an intuition of what this thermal normalization that I saw you mentioned the paper by Chen Lin et al. What would that be in holography? I mean, how would that look like?
Well, I mean, you would have to do 1/n corrections, right? So thermal fluctuations would have to come into the game.
Is it just 1/n corrections?
You definitely need 1/n corrections, yes. So that you will see some kind of thermal noise there. I wouldn't know how to do it, to be honest. I mean, it will be. I know how to tell you how to do it. I'm not sure.
One quick one.
I can ask a tangent question now.
Yeah.
So here we were talking about this mass of the magnitude, the potential for the magnitude as a phase transition as essentially the order parameter for the phase transition.
Right.
Right. But there's this other VKT like story, right, where you sort of mediate the phase transition between fluid and superfluid using vortices.
That's slightly different,
Right.
I guess. Yeah. Are you asking whether we could do that?
Yeah, I mean, I'm just saying, like, is that something also you can sort of try now? Because that is also, I mean, it's in higher dimensions. I mean, but you can.
In 2 dimensions,
Yeah,
for
in
example.
2 dimensions.
I haven't thought too much about that, even though it's a very interesting question, I guess. It is a different kind of transition.
Yeah, it's a different kind of transition, but also between the fluid and the superfluid.
Yes, that's right, yes.
Okay. Yeah, I was just asking if you had thought about that.
No, I haven't. I would find it interesting, though.
Okay.
And we thought we're out of time. We'll send guys again.
Thank you.